Have you ever wondered why large passenger aircraft store their fuel in the wings? At first glance, it seems counterintuitive. It would make more sense to store fuel inside the fuselage. There's more space, better protection, and a structurally stronger environment. But in aviation, decisions aren't made based on intuition. They're the result of precise calculations, and storing fuel in the wings is one of the most deliberate engineering choices in an aircraft's design. When people try to explain it, the answers are usually simple. The first is space efficiency. The fuselage is packed with passengers, cargo, and systems, so fuel is moved into the wings. The second is that wings have unused internal volume that can be utilized. Both explanations sound reasonable, and to some extent they're true, but they don't explain the real reason. If this were only about space, fuel could be stored almost anywhere, in the lower fuselage, near the tail, or distributed across multiple tanks. But engineers don't do that, because the real question isn't where fuel fits, it's how its position affects the aircraft in flight. We're not just talking about storing fuel, we're talking about distributing tens of tons of mass inside a flying structure, and at that point, the problem changes. It's no longer about available space, it's about where that mass will have the least impact on stability, control, and efficiency. To understand that, we need to look at one of the most critical concepts in aviation, the center of gravity. For an aircraft, this is absolutely crucial. If the center of gravity moves too far forward, the aircraft requires more control force to maintain its pitch. If it shifts too far aft, the aircraft becomes less stable and more sensitive to disturbances. In both cases, control loads increase, fuel efficiency drops, and overall stability suffers. That's why engineers carefully calculate how every major mass is distributed inside the aircraft, and fuel is one of the largest. In large airliners, we're talking about tens of tons. But there's a key difference. Unlike passengers or equipment, fuel is not constant. It's continuously consumed, which means the aircraft's mass distribution changes throughout the flight. That's the core problem. So engineers place fuel where its consumption has the smallest possible effect on the center of gravity. And that location turns out to be the wings. They sit close to the region where lift is generated and near the aircraft's allowable center of gravity range. As fuel is burned from the wings, the aircraft's balance changes only minimally. As a result, the aircraft remains stable, predictable, and efficient throughout the entire flight, without constant corrections. But even that doesn't explain everything. If this were only about center of gravity, fuel could be stored in the central fuselage and still work. Yet in reality, most of it is still stored in the wings. When you look at a wing from the outside, it seems thin, almost empty. But in reality, it's a complex load-bearing structure. Inside the wing are spars, ribs, and structural elements that define its strength and aerodynamic shape. And between them, there's a significant amount of internal volume. The key point is, this volume already exists. It's part of the structure. It doesn't need to be added or redesigned. Now compare that to the fuselage. The fuselage is the most valuable space on the aircraft. That's where passengers, cargo, and critical systems are located. Every cubic meter inside it directly affects the economics of the flight. If you use that space for fuel, you lose payload, either passengers or cargo. The wing doesn't have that limitation. That's why aircraft use what's called a wet wing design. Instead of placing tanks inside the wing itself becomes the fuel tank. It's sealed, segmented, and designed so fuel can move smoothly inside without sudden shifts. This allows engineers to use a large volume without increasing the size of the aircraft and without sacrificing payload. But there's another factor, and this is where the design becomes truly elegant. During flight, the wing is under enormous stress. Lift acts along the entire span of the wing, pulling it upward. At the same time, most of the aircraft's mass, the fuselage, passengers, cargo, is concentrated in the center, pulling downward. In simple terms, the wing behaves like a cantilever beam trying to bend upward. Now imagine that wing is empty. The bending moment increases. Stress at the wing root, the most critical structural area, becomes significantly higher. Now add fuel. Fuel is distributed along the span of the wing, acting as a counterweight to the lift force. And this changes everything. The wing bends less, structural stress is reduced, material fatigue decreases over time. In other words, fuel is not just energy, it's part of the aircraft's structural system. To see how this works in practice, let's look at one of the most common airliners in the world, the Boeing 737. It has 3 main fuel tanks, 2 in the wings and 1 central tank located in the center wing box. On short and medium-haul flights, the aircraft typically uses only the wing tanks. The center tank is used when additional fuel is required. And here's a key rule. If there is fuel in the center tank, it is used first. This isn't random. It's controlled by the fuel system logic and feed priority, not just pressure differences. Once the center tank is empty, the system automatically switches to the wing tanks. The reason is simple. Fuel in the center adds extra load closer to the fuselage, so engineers aim to remove that mass as early as possible and return the aircraft to a configuration where most of the fuel is in the wings. Even the fuel burn sequence is designed to maintain optimal balance and load distribution. How aircraft are fueled and what fuel they use. Aircraft are refueled through a dedicated fueling port, usually located under the wing. From there, fuel is pumped through the system, first into the wing tanks, and then, if needed, into the center tank. The entire process is carefully controlled and calculated in advance based on aircraft weight, flight distance, and safety requirements. The fuel itself is aviation kerosene. This isn't just regular fuel, it's a highly standardized mixture with very specific properties. It must remain fluid at extremely low temperatures at high altitude, resist crystallization, burn consistently, and ensure stable engine operation under a wide range of conditions. But just as important as the fuel is the system that handles it. Aircraft fuel systems are designed with multiple layers of redundancy. Each tank has multiple pumps, backup feed modes are built in, and the tanks themselves include systems that reduce the risk of fuel vapor ignition. So this isn't just fuel storage, it's a highly engineered, fault-tolerant system. Why aircraft sometimes dump fuel? In some situations, an aircraft may need to dump fuel during flight. At first, that sounds counterintuitive. Why get rid of something you need to stay airborne? The answer comes down to weight limits. Aircraft have 2 key limits, maximum takeoff weight and maximum landing weight. And the landing weight is always lower. If a plane needs to return shortly after takeoff, it may be too heavy to land safely. In that case, there are only 2 options, either stay in the air and burn fuel or dump it. Some aircraft are equipped with dedicated fuel dump systems. Fuel is released through nozzles, usually near the wings, where it disperses into fine droplets and rapidly evaporates in the airflow. It's important to understand, this is a rare procedure, used only when necessary. From an environmental perspective, it's not ideal, but there's a key detail. Fuel dumping happens at high altitude, where the fuel atomizes and evaporates, making it extremely unlikely to reach the ground in liquid form. On top of that, these procedures are strictly regulated. They are performed in designated areas and under controlled conditions to minimize environmental impact. And this is exactly what makes aviation so fascinating. The most important systems are often the least visible. Fuel inside the wings, load distribution, structural balance, all of it works quietly in the background, shaping how the aircraft behaves in flight. But there's another moment where engineering becomes even more obvious. Not in the air, but right at the moment the aircraft meets the ground.
Imagine the moment an airplane lands. A massive machine weighing hundreds of tons approaches the runway. Even at this stage, the aircraft is still moving extremely fast. Typically around 250 to 270 kilometers per hour. That's roughly the speed of a car racing down the highway at full throttle. And then the plane touches the ground on relatively small wheels. If you look at an aircraft from the outside, those wheels seem almost tiny compared to the enormous fuselage. The aircraft carries hundreds of passengers, tons of fuel, cargo, and equipment. Altogether, that weight can easily reach hundreds of tons. And at the moment of landing, a huge portion of that weight is transferred directly onto the tires. Which raises an obvious question. Why don't these tires explode? If a regular car tire hit the ground at that speed while supporting such weight, it would likely fail almost instantly. But there's another unusual detail. Aircraft tires are not filled with regular air, like car tires. So how can these tires survive such extreme loads and temperatures? And what role does the gas inside them play? The answer lies in two key things: the construction of the tire itself and the conditions it operates under. To understand this, we first need to look at what actually happens at the exact moment an airplane touches the runway. As the aircraft approaches the ground, it is still moving forward at high speed. But there is one important detail that many people never notice. The wheels are not spinning before touchdown. While the plane is in the air, the wheels hang below the aircraft and remain almost completely stationary. The instant the tires touch the runway, something dramatic happens. Within a fraction of a second, the wheels must accelerate from 0 to the same speed as the aircraft. In other words, the aircraft is already moving forward at around 250 kilometers per hour, while the tires initially slide along the runway until they spin up to match that speed. That's why, right after touchdown, you often see puffs of smoke coming from the tires. This isn't a malfunction, it's simply the result of intense friction between the rubber and the runway surface. During those first moments, the tires experience several extreme stresses at once: the massive weight of the aircraft, intense friction against the runway, rapid acceleration of the wheels, extreme heat buildup in the rubber. In just a few seconds, the surface temperature of the tire can reach 150 to 200 degrees Celsius. For a normal car tire, conditions like that would be catastrophic, but aircraft tires are specifically designed to operate in this environment. And the secret isn't just the strength of the rubber itself. Another crucial factor is how the aircraft's weight is distributed. At first glance, it might seem like airplanes have very few wheels. But if you look more closely, you'll notice there are actually far more than most people expect. For example, medium passenger aircraft typically have 6 to 12 wheels. Large airliners often have 14 to 22 wheels. The largest aircraft can have even more. This is done for a very important reason. An aircraft can weigh 300, 400, or even 500 tons during landing. If that entire weight were supported by just a few wheels, the pressure on each tire would be enormous. So engineers distribute the load across many wheels. There's another detail as well. When the aircraft lands, it doesn't touch down on all its wheels at once. The main landing gear, located under the wings or near the center of the fuselage, touches the runway first. These wheels carry about 90% of the aircraft's weight during landing. The nose gear, the smaller wheels at the front, touches down a moment later and mainly helps with steering and stability. This design spreads the forces more evenly and significantly reduces the load placed on each individual tire. But even with this distribution, the stress on each tire is still enormous, which is why aircraft tires are built very differently from car tires. What are aircraft tires made of? At first glance, an aircraft tire looks somewhat similar to a regular car tire, but internally, the design is far more complex. An aircraft tire is not just a block of rubber. It's a multi-layer engineering structure where each layer performs a specific function. The outer structure is made from special synthetic rubber designed to withstand intense stress, friction, and heat. But rubber alone isn't strong enough. Inside the tire are multiple reinforcing layers that dramatically increase its strength. One of the most important components is nylon cord layers. These are strong fibers arranged in layers within the tire. They prevent the rubber from stretching or tearing under heavy loads. Another key element is reinforcing fibers, which help distribute pressure evenly across the entire structure of the tire. In addition, aircraft tires contain steel belts. These give the tire extra rigidity and help it maintain its shape even under enormous loads. Thanks to this multi-layer construction, a single aircraft tire can support tens of tons of weight. At the same time, it remains flexible enough to absorb the impact of landing. Another major factor that makes aircraft tires so strong is the extremely high pressure inside them. For comparison, a typical car tire is inflated to around 30 to 35 pounds per square inch. That pressure allows the car to ride comfortably while keeping the tire in proper contact with the road. Aircraft tires operate under completely different conditions. The pressure inside an aircraft tire can exceed 200 psi, roughly 6 times higher than the pressure in a standard car tire. But this raises another interesting question. If the pressure inside the tire is so high, Why aren't aircraft tires filled with regular air, just like car tires? At first glance, it might seem like ordinary air would work just fine. After all, that's what we use in vehicle tires every day. But aviation works a little differently. In reality, aircraft tires are almost always filled with nitrogen. This isn't a random choice or an engineering preference. It's directly related to the extreme conditions aircraft operate in. During landing, the tires experience intense friction and can heat up very quickly. At the same time, aircraft regularly fly at altitudes of around 10 kilometers, where outside temperatures can drop to around -50 degrees Celsius. Under conditions like these, regular air inside the tire could behave unpredictably. So engineers chose a gas that performs better under extreme temperatures and high pressure. That gas is nitrogen. There are several reasons why nitrogen is used, and each one relates to safety and reliability. First, nitrogen contains no moisture. Regular air always contains some amount of water vapor. At high altitudes and very low temperatures, that moisture can freeze into ice. Inside an aircraft tire, that is something engineers want to avoid. Using dry nitrogen eliminates this risk. Second, nitrogen contains no oxygen. Oxygen can react chemically with rubber and metal components over time, which can accelerate material degradation. Removing oxygen helps extend the life of the tire and wheel components. Third, nitrogen pressure behaves more predictably when temperatures change. During landing, the tires heat up rapidly due to friction with the runway. Nitrogen helps maintain more stable pressure levels inside the tire, even as temperatures rise. And finally, nitrogen is safer in extreme conditions. It does not support combustion, which makes the entire system more stable under high heat and heavy loads. For these reasons, nitrogen has become the standard gas used in aircraft tires. It's the combination of all these engineering solutions that makes something seemingly impossible actually work. Those relatively small wheels are capable of absorbing the landing of an aircraft weighing hundreds of tons while traveling at more than 250 kilometers per hour.